So with this problem here, let's modify it like I made that modification in class. So let's just get rid of that right there. Okay, now let's count how many sp2 hybridized carbons there are. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How would you use IR to determine if the following reaction was successful? So when you look at that, what's changing? We're simply going from a carbonyl to an alcohol. So this carbonyl stretch has to disappear, and this OH stretch right there, that stretch between that oxygen and hydrogen, has to increase. And so what you're seeing is answer C. The appearance of 32 to 36, which is the alcohol stretch, and the disappearance of 1720 is the carbonyl stretch. Which one is this? And so what do we do? These numbers are very pixelated. Not very, very good, are they? So if I go down 3000 right there, we have signal right there. That is going to be our carbon-hydrogen stretches with the sp3 hybridized carbon. Okay. Let's see, we have some signal right there, implying that we have a nitrogen with 2 hydrogens. So that's kind of what we're going off of. When I see some of the examples here in the answer choices, I see carbonyl, carbonyl, carbonyl. And so there's no big stretch around 1700, so I can just automatically eliminate those guys. Okay. And then it's just left between 3 and 5. And this nitrogen species has 1 proton that has 2. Because of that signal right there. Also, I don't have any carbon double bond stretches or the sp2 carbon hydrogen stretches. So that would be the correct answer. In each pair, which one has the weaker carbonyl stretch? Well, pair 1, you have to say which atom, this nitrogen or this oxygen here, which one is more likely or more willing to donate its electron density in, like that. And the atom that can do that the best, or the strong, how can I say that? The atom that's more willing to use its lone pairs to resonate in will weaken that carbonyl stretch right there. So we know that oxygen is more electronegative than nitrogen. And so it's going to hold on to its lone pairs tighter than nitrogen. So nitrogen's going to be more willing to resonate in, hence weakening that carbonyl stretch. So what do I mean by weakening? It's going to give it more single bond character. Because when you draw the resonance structure, when that nitrogen donates hydrogen or electron density in, you're going to get this species right there. And when you compare this bond right there to that double bond, you can see that I've weakened it in the sense that it doesn't have as much double bond character in that resonance form. So we're going to have a weaker carbonyl stretch for A. We've also learned in pair 2 that when you have conjugation, that weakens that carbonyl stretch, so that's the weaker one. And then in E and F, we're comparing nitrogens, so that can resonate in this way, or it could resonate in the other way. Okay, it can't really do both at the same time, let's say. And so if it resonates with the red arrows, then you have beautiful double bond character there. If it resonates to the right, shown in the green arrows, we have double bond character there. So it's like this species right here is always going to have more double bond character because you have 2 of them. Whereas F, all of the electron density on that lone pair is going to resonate in. Okay, so that means this carbonyl stretch is going to be more weaker, or that signal is going to be weaker because there's only 1 carbonyl. So 4 would have to be answer D. Rank the following bonds with highest to lowest wave number. So what does wave number imply? That implies IR. So now we have to use Hooke's law, the oversimplified one. And we can see if we compare these 2 right there, which one's going to give you the lower signal or the smaller wave number between those 2 that I just put in the rectangle. Well, D is deuterium, which is an isotope of hydrogen, so that's going to be heavier than hydrogen. So the M value right here is going to get larger. And what's that going to do to the frequency or the wave number? Make it smaller. A larger number in the denominator makes the value smaller. So between 3 and 4, D is going to give you the smaller signal. Okay, and then if you compare between these 2, chlorine is much larger than oxygen, hence this one will be smaller, give us a smaller wave number. So then when you put it all together and compare all of them, you're going to see that the answer is A. Okay, because nothing is changing about the spring constant. Spring constant, or the K right there, looks at when you have double bonds, triple bonds, and single bonds. So hence the hybridization states have changed. But all 4 of these examples right here, they're the same hybridization state in theory. Okay, so that is saying that that's the highest, that is the lowest. Which best describes the mass spectrum of chlorocyclopentane? The answer for that one is, since we know that we have chlorine, we have the isotopic ratios of the M and the M+2. And they have to be what? In a 1/3 ratio, because it's chlorine. So that would be that answer. Which of the following compounds is most likely to show a prominent peak of M-29? M-29 is what? What species is falling off? CH2, CH3. What is that? That's 12 plus 12 plus 5. So 24 plus 5 equals 29. So M-29 is a ethyl group. And when we take a look at our molecules here, where's an easy ethyl group that can pop off? Right there. We can cut that bond, and now we're left with an ethyl group that has fallen off. And so answer A would be the correct answer. If a molecular ion peak is even, is it possible to have a nitrogen in the molecule? Yes, it is. Because if you have an odd number of nitrogens, the mass spec or the molecular ion peak is going to be odd. If you have 2 or an even number of nitrogens, it will be even. But it's also not possible. Well, it is possible. Well, let's just read the question as is. It is possible, but not a guarantee. How many of the following molecules cannot undergo McLafferty rearrangement? So the McLafferty rearrangement simply means that you have to have a proton on the gamma carbon. So if we look at these things here, we have alpha, beta, gamma. Are there hydrogens on that gamma? Yes, so that can. Alpha, beta, gamma. Oh, the gamma. Let's do gamma. Are there protons there? Yes. Alpha, beta, gamma. Are there protons? Yes. So those work. That works. That works. Alpha, beta, gamma. There's no protons, so that one does not work. Alpha, beta, gamma. There is a proton coming off, so that does work. How many degrees of unsaturation does this molecule have? You have one for the ring, second ring, third ring. So that's 3, 4, 5, 6, 7, and 8. Write the chemical shift from the visible proton from smallest to largest. Which one's going to be the the smallest. So my brain just likes to look at it from the greatest here. Let's see here. So right from the start, I can see that this guy's going to be the greatest. Wait, am I misreading this? Let's take a pause here. Rank the chemical shift from the visible proton from smallest to largest. Well, when you look at molecule B, that proton is adjacent to some very electronegative atoms, right? So that's going to de-shield it. So that's going to have that proton right there is going to be the most de-shielded. So that has to have the greatest chemical shift. And then the next one would be A. So we'll go by numbers. That's the greatest. That's the second. And then that would be third. And then that would be the fourth. So now we just have to think about that in reverse, right? So when we're looking at these inequalities here, what's the weakest or the smallest chemical shift? It would have to be D. D, C, A, B. So that would have to be that answer right there. Which of the following best describes the difference between the methylene hydrogens? So those. Wait. Let's see. It's saying the methylene hydrogens in the ethoxy group, and the methylene hydrogens in the ethyl group. So we're comparing those two. Which best describes those? And the answer is D. The ethoxy group is further downfilled because it is de-shielded by the oxygen atom. Yes, it's further downfilled from the methylene right here because of that oxygen. How many signals would you expect for the following molecule? Remember, what is the hybridization state of that carbon? We see that it's sp3. So Do you have 3 bonds all in the same plane? No, you don't. You know that you have to have the stereochemistry. You also see that that is a stereocenter. So you have to have wedges and dashes. Now, is it the R or the S isomer? I don't know. It doesn't tell me. But I'm here just to predict signals. And so we have 1. Oh, let's draw in all the hydrogens too. We have some right here, right there. So a common mistake would be this one. 1, 2, 3, 4, 5 signals. Can you see why that's a huge mistake? Because these protons right here, right there, those are diastereotopic. That would give us 2 distinct signals. And so we would actually have, what, 6? 6 signals. Now, how do you know they're diastereotopic? Well, you can look down this backbone right here and see that there's no plane of symmetry. Or if you do the replacement test, the relationship between those 2 species is going to be diastereotopic. So we'll draw in just that, X, like that. No, that one's the X. Okay. Now if we just say that's molecule A and that's molecule B, what's the relationship? Can I superimpose them? No. Is there a mirror image? No, there's not. If you take this and flip this 180 degrees, everything is a mirror image except for this is now a dash when you rotate it 180 degrees on the vertical axis. Which compounds gives the following proton NMR? So I've spelled it out for you, showed you the integration and the splitting pattern. So now we just really just look at the answer choices and make sure that it all matches up. And what I see right out of the gate is that we have a broad singlet that integrates for 1, most likely talking about a hydrogen attached to an oxygen atom, since those are our answer choices. So I'm going to say answer choice C is off the table because there's no broad singlet in that molecule. That's an ether. So we want to look for some alcohols here. I see some signal in that region right there. So that's implying that we have a benzene ring. But look at what the splitting pattern is. We have a doublet and a doublet. Okay? So that is implying that when you have a benzene ring, well, let's draw it over here. When you have a benzene ring, what type of substitution pattern do you have? I don't know what's attached to it, but or we'll call that Y. Look at that. In that substitution pattern, this disubstituted benzene, do you see how these protons right there are equivalent? And these are equivalent to one another. Now, why am I saying A and B? Because I fixed this. I'm saying this is going to be a different group. So X and Y are different. And so you can see with the A protons there, those have to be doublets. Okay. And B also has to be a doublet. If you change the substitution pattern to something like this, what is it going to be? We have proton there. That's going to be A. That's going to be B, C, and HD. So that's going to have 4 distinct signals in the benzene region. And the splitting pattern is going to be what? A will be a doublet, D will be a doublet of a doublet, C is a doublet of a doublet, and B is a doublet. And that's not the splitting pattern that we see in our spectrum. So based off of that analysis, what we can say is, hey, we got to get rid of everything that's not a para-disubstituted species. So this is just a monosubstituted species, D, so that's off the table. B is a meta-disubstituted species, so that one's off. And A is the only one that's a para-substituted. Now when we delve in deeper, that matches, but now do we have a quartet that integrates for 2? We'll call that, let's call that C. And we can see C is right there. No, wait, quartet. Yeah, that works, sorry. And then D be that proton. So that all lines up beautifully, giving us that as the answer right there. Okay. Okay, what do we do with this here? Now, I don't have a calculator with me. Let's see if we can do this in our heads. Okay. So we have C5H8. That is a chlorine, nitrogen, oxygen. So C5H, we're adjusting it. What are we supposed to do with the 8 protons? We're supposed to add 1 for every halogen. We're supposed to subtract 1 for every nitrogen and do nothing for the oxygens. So what do we have? 8 plus 1 is 9, minus 1 is 8. So our adjusted formula looks like this. And then we take that formula, 2 times 5 plus 2 equals what? 12. Then we subtract that value, which is 8. And then that would equal what? 12 minus 8 is 4. And then we have to take that value and divide it by 2. Why do we have to divide it by 2? Because for every 2 missing hydrogens, we get a degree of unsaturation. So that's 2 degrees of unsaturation for that. So since we have 2 degrees of unsaturation, we now can draw 2 possible structures. And the sky's the limit with this one. So first thing that I'm going to do is I'm going to draw 5 carbons. 2, 3, 4, 5. It says I need a halogen, so I'll just stick it there. I have an oxygen, so I can do a double bonded O. And let's see, we need a nitrogen, so I'll just stick one right here. But how many hydrogens does nitrogen have to be neutral? 2 in that situation. And then, do I have an oxygen? Yes. Do I have a nitrogen? Yes. Do I have a chlorine? Yes. Do I have 5 carbons? 1, 2, 3, 4. Not anymore. So let's add a carbon. Now I have 5. And do I have 2 degrees of unsaturation? No, I don't. I only have 1. So let's just add 1. There, I have an alkene. So, do I have 5 carbons? 1, 2, 3, 4, 5. Yes. Do I have 8 hydrogens? 2, 3, 4, 5, 6, 7, 8. Do you see how I'm doing this structure right here off the cuff? Like, I'm not thinking that hard about it. It's just 5 carbons, draw them out. So let's do it again because we need 2 of them. Okay, 5 carbons. What if I drew a 5-membered ring? That's 5 carbons. And a ring counts for 1 degree of unsaturation. So what do I have to do? I'll do another one like that. So that's 2 degrees of unsaturation. Now I need to find tack on a chlorine and a nitrogen. I already counted 5 carbons. I have 1 nitrogen and 1 oxygen, 1 chlorine. Now I just double check the hydrogens. 2, 3, 4, 5, 6, 7, 8. And that matches the chemical formula. Okay, what are the predicted splitting patterns for the protons? So A has to be a singlet. B has to be a triplet. C is a complex splitting pattern. That would be a quartet of triplets. And D would be a triplet as well. Now let's explain the splitting pattern for C. We have protons right there. And then we have our protons right there. Now we've realized that these are equivalent and those are all equivalent. So when we look at the splitting pattern for the protons attached to carbon C, we have to go to the adjacent carbon. And there are 3 protons. 3 plus 1 is a quartet. We go to that adjacent one. And there are 2 protons. 2 plus 1 is 3, making that a triplet. Why is this not called a sextet? Because there's a total of 3 plus 2 is 5. 5 plus 1 is 6, which is a sextet. Why is that wrong? Because you only add up the protons that are equivalent to one another. You cannot add those 5 protons together because 2 of them are A and 3 of them are B. They're chemically distinct. Okay? So if I ask another question to you, would you be able to answer? What's the relationship between these A protons? Homotopic or enantiotopic? Hopefully all of you are thinking enantiotopic. Yeah, because there's a plane of symmetry right down that molecule. If you take this molecule here and rotate it out of the plane by 90 degrees and just look straight down that carbon skeleton, you will see that those 2 protons are on either side of that plane and are going to be enantiotopic. Why are they not homotopic? Because there's no axis of rotation. 17 here. What's the splitting pattern for these guys? Okay, let's start off with the easy one, D. That's just going to be a broad singlet. Let's see, protons B. Its neighbor only has 1 proton, so B has to be a doublet. Okay, let's draw in the hydrogens that are implied. And then we have to ask ourselves, are those 2 protons that I just drew, are they equivalent? No, they're not. Because they're diastereotopic, because they are next to a stereocenter. So if we ask what is the splitting pattern for C, that's going to be a complex splitting pattern because the C proton is attached to this carbon. What's adjacent to it? That one. How many protons are on that one? 3. 3 plus 1 is a quartet. The C proton is attached to the carbon with a solid dot, which is also adjacent to that one. And we see that we have an X and the Y proton. So X is going to split C into a doublet. And proton C is going to be split by proton Y as a doublet. Like that. Whoops. Is there an undo button on this thing? Nice. Let's get rid of those. Okay. So let's say, what is the splitting pattern for E? Well, that's going to be a complete mess. E proton is attached to that carbon, so we have to go to the adjacent. And we can see that there's 2 non-equivalent protons, so that X is going to split into a doublet. Y is going to split that into a doublet. Okay. Now we have to go to the other adjacent carbon. And are these 2 protons equivalent? Heavens no. So we can give those 2 distinct symbols. We'll just say proton 1, proton 2. Those are chemically distinct protons. They're diastereotopic. And so if we continue on, proton E is going to be split by proton 2 as a doublet. And E is going to be split by proton 1 as a doublet. So we have, if we condense that, we have a doublet of a doublet of a doublet of a doublet for proton E. And then, let's see, proton A. What's that going to be? Let's clean this up here. Okay, I'll leave that purple there. So proton 1 is attached to that carbon. What's the adjacent carbon? That one. And so that's going to split, proton E is going to split A into a doublet. But remember that proton 1 is attached to the carbon as indicated by the solid dot, but it's also attached to proton 2, which is not equivalent. So that is going to split proton 1 as well into a doublet. So that's what the splitting patterns for that guy would be. Okay. Let's see here. Hey, 18. One of these figure it out type things. Okay, first thing that I do, I see that I have the molecular formula right there. So I'm going to calculate the degrees of unsaturation. So 2 times 9 plus 2 is what? 20? 2 times 9 is 18 plus 2, 20. Perfect. Minus 10 protons equals 10. Divided by 2 equals 5 degrees of unsaturation. So that's, 5 degrees of unsaturation. Okay. Now we look at the IR. If I split right down 3000, I have some signal right there, implying that we have some carbon-hydrogen stretches that are sp2 hybridized, or sp3 hybridized, like that. We have a beautiful carbonyl stretch right there. Okay. And then I have, looking like I have some signal right there for some carbon-carbon double bonds. So that looks promising. Okay. I can say there's not going to be any alcohols because there's no broad peak there. And just by looking at the IR, that's what I come up with. But then when I take a look at the proton NMR, I see a singlet around 10. And so that's screaming aldehyde. And so when I see that as an aldehyde, potential aldehyde molecule here, functional group here, I can then now go back to my IR and see that I have signal there. The proton for the aldehyde is going, there's going to be like a doublet up there in the IR around 2700 and 2800. There's going to be those two peaks there, and those are there. And so that, seeing that signal there, integrating for one proton and then signal there is making me really confident that I have some aldehyde in my molecule. I also have a, what is that? A doublet and a doublet in that range of 7 to 8. So that little piece right there is screaming benzene. But what type of benzene? And by the splitting patterns of two doublets, I am pretty confident that I have a para-disubstituted benzene. Okay, and then when I look at that signal right there, that integrates for 2, so that means I have a methylene that's attached to something that's going to give me a quartet. So that would mean it would have to be attached to a methyl. and I don't know what it's attached on that side. And then when I look at that signal right there, integrates for 3 and a triplet. And that methyl group's adjacent to a methylene, which would give me a triplet. So I'm thinking those are my pieces. Okay. And so how can I put this all together? Well, I know I have a benzene ring that's disubstituted, and I have 2 groups. And I have 2 groups here. I have something that looks like an ethyl and an aldehyde. And it's disubstituted. So if I start with a benzene ring, could I attach a aldehyde to one side and an ethyl to the other? Does that match the splitting pattern in my prediction? I'd say this proton, that's A, that's B. And A and B, A has to split into a triplet. B has to split into a quartet. Then I have these protons right here. And those would be C. Those are D's. Those can't be equivalent. And then we have E for the aldehyde proton. C, I predict to split into what? A doublet. And D, I would predict to be split into a doublet as well. So that matches the splitting pattern in the proton NMR very nicely. Do the chemical shifts make sense? Let's see. We have the B protons right here that are right next to that benzene ring. That's going to make that further downfield than the A protons. That makes sense. The E proton here on the aldehyde should have a chemical shift around 9 or 10. That makes sense. And then these protons right there are in the benzene ring, so that should be around 7 to 8. So the chemical shifts make sense. And so let's annotate this now, clean this up. Okay, so we can say that that has to be the A protons, B protons. And we would expect the D protons to be further downfield because they're next to the carbonyl on the aldehyde. Proton C would be a little further upfield. And then proton E for the aldehyde. That all lines up beautifully. So now if we annotate the carbon 13, we can see that we have that species right there. That carbonyl, that's going to be the one that's furthest downfield. And we're going to have to label that with a different letter, so F. Okay. And how many carbons do we have here? Signals do we have? Let's double check that real quick. 1, 2, 3, 4, 5, 6, 7. And how many carbons do we have in our... We have 9 carbons. So we can't freak out, say, oh, that's just wrong. Because there's supposed to be 9 carbon. There's 9 carbons. Does not always mean we have 9 signals in the carbon 13. When we take a look at our proposed structure here, we can see that these carbons right here, they're equivalent. And then these 2 carbons right here, they're equivalent to one another, but not equivalent to the green ones. Okay, so we have 2 right there that are similar. Okay, and then we have this carbon right there, and find another color here. Let's go purple. And that carbon right there. So in the benzene ring, we have 6 carbons, obviously, but we only have how many signals? 1, 2, 3, 4. We would expect 4 right there. Okay. And so we see 1, 2, 3, 4. really downfilled, indicating those are the benzene carbons right there. And then we would say that's carbon B, and that's carbon A right there. Now, would you be able to figure out which carbons these are in the benzene ring? Yeah, you could. You definitely could. Let's take a look at it. So based off of, let's do some numbering here. Well, maybe we could do colors. Where would you expect that light blue one to show up? Right there. Because it's next to F. So the green ones right there would be next. And then the red ones would be next. And then the last one. Okay. Perfect. So the unknown molecule is that one right there that I have drawn. And in order to get points for a question like this, you see the level of detail that I'm describing here. Oh, another thing that I forgot to mention, when we look at our proposed molecule, does it have 5 degrees of unsaturation? Yes, it does. So that everything matches up beautifully. So that right there is the answers to that assignment there.